We've talked a bit about bottled water. Let's look at the bottle itself now. And the world of plastics and polymers is something that's hard to imagine if you are less than 30 years old, because they have just the whole area of polymer chemistry has just exploded since World War II and the 1950s especially. Developed about 150 years ago, plastics have been designed to be moldable. That's where the word plastic comes from. The Greek word plastikos means to mold. Plastics are typically organic polymers, and we're going to look at what a polymer is. We're going to see synthetic as well as natural polymers, especially in the world of nutrition. They have high molecular masses. They are often doped with other substances. And for us, we are going to look at synthetic, in fact, mostly derived from petrochemicals, though some are partially natural. Right now, you're probably wearing a dozen different plastic materials. You are in vision of probably another 30. And most of these did not exist 75 years ago. Some were around 10 years ago. And they have made our lives immeasurably more comfortable and safe. So that's why plastics are important. We also want to look at what happens to them when we are done with them. Some things we touch for barely a moment, like going to Subway and they put it in a plastic wrap, and then you take it out of the plastic wrap as soon as they hand it to you. And then it's just thrown away without a second thought. Other ones are used for decades and decades. What happens to the ones, though, that are recycled? If you are, in fact, from a child of the 50s, you may have seen...
Ben, excuse me. Mr. McGuire. Ben. Mr. McGuire. Come with me for a minute. I want to talk to you. Excuse us, John. Of course. Thank you. I just want to say one word to you. Just one word. Yes, sir. Are you listening? Yes, I am. Plastics.
This is from The Graduate, mid-60s.
Exactly. How do you mean?
There's a great future in plastics. Think about it. Will you think about it?
Yes, I will.
Enough said. That's a deal. So, what do you think of when you hear the word plastic? Besides someone who is not sincere. Oh, we have them in our bottles. We have them in our wrap. And we know that they are everywhere. Rayon, nylon, lycra, polyurethane. See that word poly? That is a clue to where we are going. We have poly. That is important. Teflon, styrofoam, saran, as you know, probably is saran wrap. But plastics are polymers, so let's talk about what a polymer is. Poly means many, and polymers are large molecules made up of long chains. Those look like the paper chains you made in elementary school at Halloween, but they are long chains of atoms bonded together covalently. Remember, these are going to be predominantly hydrocarbons. That's carbon and hydrogen. So we're going to see covalent, not ionic bonding. Monomers. This is from the word mono, meaning one, meros, meaning unit. They're small molecules used to synthesize polymeric chain, like the strand of paper clips. And it is the monomer that makes the important properties, many of the important properties of the polymer. How they're arranged also is important. Polymers, yeah, they've been with us since the beginning of time. There's a little picture of grass. Grass is a cellulose, a polymer. Natural polymers, plants and animals, Proteins, those are polymers of chains of amino acids. Complex carbohydrates like cellulose, starch, glycogen. Oh, we're going to see a lot of those in chapter 11. See how they're arranged using the same basic atoms, carbon, hydrogen, and oxygen. But boy, how they're linked together makes a big difference on even whether you can digest them. Humans can't digest cellulose, but we can digest starch and glycogen. That is, chemically change them during our metabolism. Natural rubber, tar and shellac, tortoise shells, and horns. The list goes on. Natural, they began to make them chemically modified. Most famous of these were vulcanized rubber, cotton, and celluloid, and these were in response to improving properties, vulcanized rubber, and also shortages. When they could not get a hold of enough rubber, they started working on that. The first semi-synthetic means man-made, not natural, was Bakelite in 1909. And then we've got the first fully synthetic was rayon. That was developed in 1911. And like I said, they provided economic substitutes, things that were cheaper, more readily to make than even the natural. All right, so let's look at polymers. Polymer means many and can be formed from the same monomer, or a combination of monomers. So if we look at A, the little blue box is a monomer, and then B shows a representation of a polymer made from one monomer. We're going to look at those chains in just a second. And then the last one, C, is a representation of a polymer of two different monomers. This guy is called I must come down here, get my pen. This is called a copolymer when it's made from more than one monomer. In polymerization, N, that's just a generic number of molecules of the monomer. In this case, it's ethylene. Down here is, this is the monomer ethylene. If you remember, the ethyl means two carbons, and this one is, because it's got a double bond, remember, carbon prefers to have 4 bonds. If 2 of those bonds are a double bond, then we need less hydrogen, single bonds, and so we find the formula here, as opposed to ethane, is C2H4. Ethane is the single bonded C2H6. So that is my ethylene, and can vary from a lot, from less than 100 to over 1 million, but they're still big. And then we have this R. R is written over the arrow because it's not really a reactant, it is a catalyst. And remember that the catalyst is an important species that may be consumed during one step and then reproduced in a later step. So little dab will do you. You don't put much in there, and he is not consumed overall. This case, he's got a little dot here, and that's to indicate to us that he's a free radical. That unpaired electron makes him very reactive, and here we go. This, you'll notice here in the product, the double bond is gone. The the addition to the ethylene occurs here and occurs here. So we have the same number of hydrogens in our resulting unit, but the carbon now has bonds to new atoms as opposed to each other. Polymers are referred to as big macromolecules because they involve thousands of atoms. Their molecular masses can reach over 1 million. They are mostly composed of hydrocarbons. Remember hydrocarbons when we're talking about fossil fuels. These are molecules containing just hydrogen and carbon for the most part. Carbon makes up the backbone. Carbon has that unique property of catenation where it can form very long skeletons of carbon bonding. So here we have poly. There she is again. There would be my default polyethylene. So that's multiple ethylene. The simplest and very widely used polymer structure. This one here, the polyethylene, they've drawn it giving you an idea of the 3D structure. Remember when we were talking about Vesper and different shapes, molecular shapes, we said that carbon takes on, if it has 4 single bonds, it will have a tetrahedral configuration. And this guy is supposed to mean that he's coming out at you, this one's coming in at you, and so it looks like a tetrahedral. Okay, other examples, polypropylene, polybutylene, polystyrene. Probably polystyrene you've heard of. Notice I chose those because they all say poly. So they've got different ways of putting the monomers together. This one is, This one is in simple addition, and she's the simplest way. Monomers are simply added to each other in the growing polymer chain, and we have all the atoms we started with. Notice that over the arrow we've left off the catalyst in this case to simplify. And as the additional ethylene molecules join, the chain grows and no other products are formed. No atoms are eliminated. We're going to see another one in a few minutes called condensation, where water is spitted out. The overall process is very simple. With that little n we can use, we say, okay, the same unit. This is not a copolymer. Oh, it's kind of boring. The double bond disappears from the monomer, and the polymer has the carbons bonded to neighbors. If one of the hydrogens on the ethylene is replaced by a chlorine, that's the Cl, then we've got, ta-da, polyvinyl chloride, PVC, which you've probably heard of in pipe, PVC pipe. This has a lot different properties, physical properties, doesn't it, than that polyethylene, which is bottles and different wraps. It is very hard and molded and used for sewage pipe. It's got low cost, high chemical resistance, and very easy to join. So I say these are hydrocarbons, but just a change of that sort is acceptable to stay within the family. Okay, now we've got condensation polymers. I bring this up because she is important for not just many common synthetic polymers like nylon, but we're going to see this exact same process when we take our monosaccharides like glucose, put them together to make sucrose, which is a disaccharide, or the more complex carbohydrates, or those polysaccharides. So what is condensation polymer? Well, condensation, you think of water, da-da, that's what it is. Another way to make polymers, you join the monomers, but you spit out water. You got starch, wool, silk, proteins, Kevlar, which is used a lot in military apparel, and you find this a lot more complex monomer. Notice I've got adiabatic acid. It's a carboxylic acid, which is this species right here, the COOH. That makes him a carboxylic acid. These are what most natural acids are. And pen color. We find that we take the OH from one neighbor and and hydrogen from, this is a copolymer. That means I got two of them. Hexamethylene diamine. And when you see the amine, you know you got some nitrogens. These are derivatives of ammonia. But anyhow, so we have monomer 1, adipic acid, monomer 2, hexamethylene diamine, and together they make what we call nylon. We've got a second product though, water, condensation.